So, welcome to this lecture. So last time we looked at the difference between classification and clustering, or you could say also in a more general way, supervised machine learning and clustering approaches. And you see that especially the input is already different. Here we just have descriptions of specific data points, and each data point describes an object. And here we have descriptions of data points in some Euclidean space, or actually also in some other geometric space, that's possible. And in addition, we have a particular marked up label. And what we want to learn is the way of labeling a new incoming object for which its position in the space is known but not the actual label. That's what we will mostly look here at classification and regression, where classification chooses from a limited set of category labels, can be very large, such as if you recognize objects in images, you might have 10,000 labels, 50,000 labels, depending whether it's a dog, a cat, or a platypus. And in regression, you have an infinite number of values because any floating number could be a possible value, or even double number could be a possible value. I just want to mention here, but we will not look into this, that there are other machine learning tasks that we don't study in this lecture. Reinforcement learning is one, that's not even here on the slide, but there's a whole lecture on that given by Matthias Niepert. Association rules is a different way of unsupervised machine learning, where there is a question, yeah? I can try to increase the volume. Is this any better? Not really. Is this any? Maybe let me try the other one. I'm surprised. So this worked well in the past. So, yeah, that's better. Good. So, yeah, you have to let me know if anything's going wrong. I'm a bit surprised because in the past also that alternative microphone worked quite well. But somehow this year it doesn't. Okay, so there are other machine learning mechanisms that we don't discuss in this lecture here, which build a lot on what we discuss here. And there are entirely different classes of machine learning. Association rules is one of them. And so what you try to find here, typical thing is you have transactions, like you purchase something in a supermarket, and then you put certain products into your basket, and then you try to find out those people, for example, who put in beer into their basket, also put in some chips, some crisps into their basket, and things like that. And once you have this knowledge, then as a supermarket owner, you can think, should I put these things together so it's easy for the customer that they buy crisps together with the beer? Or do I put them at different parts of my supermarket so they have to go through all the supermarket and then buy additional stuff? That is not answered then by the machine learning. Then you will have to make experiments. Or subgroup discovery, where you try to find groups that have certain behavior, maybe even like such kind of rules. And reinforcement learning, where you do not say really how to do things, but you give a kind of a fitness function, and you say, what do you want to achieve? For example, you want to find your way to a certain target, and then the mechanism learns to automatically find a good way towards a particular target. Good way could even mean you have a robot, and the robot learns how to use its 4 different legs, which is a very complex motion, just based on some fitness function that indicates what is a good movement, what is not a good movement. Outlier detection is one which we also have in our group, or anomaly detection. So where, for example, certain machinery works and you try to find when something is unnormal. Yeah, and you have not trained for that. You only know normal behavior. Regression, of course, we will talk about. So you can characterize a large part of machine learning, not everything. Right? Reinforcement learning is not in this picture, as either the goal is to predict, you try to predict a category or a value, or the goal is to represent, where you try to somehow have a good representation of your data, a very compact representation of your data, a representation out of which you can draw additional knowledge in some way. And typically, very often, the goal to predict goes hand in hand with the fact that some target attribute is given, or the goal to represent often goes hand in hand with the fact that the target attribute is not given. But, for example, when we talk about language model, large language models like ChatGPT, you learn to predict, but actually the target attribute is not really given. The large language models just mostly learn. The picture is a bit more complicated. We do this in our foundation models lecture. But the base learning is just you observe how words follow each other. So you don't have a specific separate target attribute. You just take each attribute that you have also as a target. So in our lecture here, all learning to predict are means of supervised machine learning, where target categories are explicitly given, categorical or numerical. Or learning to represent, well, I put this at the end, and often we don't have much time to go into unsupervised machine learning where we do clustering. Let's see how far we get this time. But as you see from these examples, supervised machine learning is not exactly the same as learning to predict, and unsupervised machine learning is not exactly the same as learning to represent. When you look at literature and also at different conferences, you will encounter notions like data mining, knowledge discovery, and machine learning. And when you then look also at the papers at these conferences, there's overlap, but there is also some distinction. And the delineation between them is oftentimes blurry and oftentimes motivated by the history, like which algorithm came from rather which kind of community. So in machine learning, the emphasis is typically on classification and regression, and the emphasis is more on the theory. That's what you find more in the machine learning conferences. In data mining, the emphasis is often more on the application or on the discovery of unknown facts and trends. These days, you may also have methods that are more biased towards efficient database access because you need to access the examples very often. The same is true for knowledge discovery. And knowledge discovery, the emphasis often is much on the process of a person interacting with the system in order to discover meaningful knowledge. They all have in common that they try to learn from data something. And they have overlapping methods also. So you can then assign some of the conferences here in this picture. You don't have to learn this picture, just that you are aware that there are these different terms and that you might find interesting resources in corresponding conferences. Now, what has been defined for knowledge discovery is a knowledge discovery process which is useful in general. And this process is a bit like a recipe, a general recipe. It's a bit like a recipe for cooking everything. Yeah? And of course, that's never quite possible, but at least you can do some general considerations of what should you do in order to prepare a cake or some meat dish, or in this case, some machine learning or knowledge discovery solution. And this whole process was motivated by the time when knowledge discovery as a kind of a subdiscipline of automated machine learning came up. And it was defined then, I think it's still a good definition, as a knowledge-intensive task. So in order to do machine learning, you have to put in knowledge. It's you cannot just push the button. There is a discipline called auto machine learning where it tries to learn just by giving it the data. But this also typically is just a starting point. So it's a knowledge-intensive task. You have to use your brains, consisting of complex interactions. Well, typically, you will try to develop a solution, and you will check the quality of the solution. You will find weaknesses. You will work on these weaknesses, and over time, hopefully, have good ideas that bring you closer to your target. So it's typically a process protracted over time between a human and a large database. Well, it can be a relational database, but it can be just a large set of documents or a large set of pictures or whatever kind of base of data you could have. And usually with a suite of tools. And now whether this is Keras or PyTorch or Weka or whatever library you like to use, this is typically what you somehow engage. The problem of knowledge discovery is that you have as input some data. Right? When you think in terms of a process or in terms of an algorithm, always think in terms of what is the input, what is the output. So the input is some data. Data can be a set of facts, examples or cases. This could be tuples in a relational database. Still, a lot of commercial applications work on, well, tuples in relational databases. It could be records in a file. Quite often, for practical reasons, you get a dump from a database, which could just be such a records in a file, could be a dump of a relational database, or text documents, or something else. And as an output, you want to have a pattern-induced knowledge. Quite often, this pattern comes with some machinery in which you can execute it. So you want to learn a categorization, and of course, quite often you want to run this categorization also. So you are interested in the pattern, how to classify, and of course you want to run this pattern in a particular classifier. So what is a pattern? It's an expression in a language for describing, for example, when we have a relational database, relations of our set of facts. And what can this expression do? Well, they can constrain the values. They could say, like we had this example last time about shoes, for all shoe sizes below 5, it holds that, right? So you would have a constraint of an attribute in order to make a statement about it. It could find relations between different database attributes. It could find rules or something which is interesting. And the pattern that you look at, the expression that you want to find, must be simpler than simply enumerating all the data. Right? If you can just enumerate the data, you don't really have something that generalizes to new unforeseen cases. Yeah, obviously, what would be a simple example? Let's say I have different kind of objects, yeah, objects like these, and if they all had an ID and it would just enumerate, this is a pen and this is an adapter, then I would not have really learned anything. I would just have memorized that this is a pen and this is an adapter. But if then the next object comes around, then of course the classifier should automatically say what it is and not say, oh, I don't know this, so I give up. So enumerating is not useful as a learning procedure. You need an expression language that tells you, something which is lengthy, has a tip, allows for writing, that's probably a pen. Now, the activities you do when you go into this interactive process includes various activities for making sense out of data. And, well, this includes this process that aims at identifying valid, novel, potentially useful, and ultimately understandable patterns in data. Now, when you're just interested in the patterns, then, of course, these patterns should be valid. If they are invalid, it means, yeah, you have patterns, but they don't apply really to the data you have. That's not very good, yeah? Typically, in knowledge discovery, you are interested in novel patterns that you don't know already. I mean, if you look at this supermarket basket and you find that beer goes along with crisps very often, then maybe as a supermarket owner you would say, yeah, I know this. I mean, I've been putting the crisp next to the beer for the last 4 decades, even before knowledge discovery was around. So you would not really discover new knowledge if it was not a novel pattern. It should potentially be useful, right? Can I make something out of that? And you somehow often want to understand it. That's not always true for machine learning. In machine learning, you sometimes don't care about it. I mean, if you achieve, and this is an ongoing discussion actually. So the question is, if I have a machine learned algorithm that tells me whether here some lesion on your skin is a melanoma, is a tumor or not, do I have to understand why the algorithm tells me that? So, and this may depend on the use case. I mean, maybe for some quick screening, all you care about is information to a doctor, please look at this critically. On the other hand, if you can also provide an explanation, this may be much more useful to the majority of users than if you just say, here's something, but I don't tell you why. So, understandability is sometimes a topic, but often not, especially with all the deep learning. When you look at ChatGPT, there's not really a good explanation why it works as it does. You can ask it for explanations and it will make up something, right? That's not what I mean with understanding what happens in the algorithm. And this all typically means that you fit a model to your data. So we will encounter this notion of model very often. Model is another way of saying that I have an expression or a set of expressions that together form a model that is an abstract description of my classifier or my regression, etc. And hopefully even finds me some structure, some high-level description of my data, which then sometimes is considered a compression of the data. And again, the pattern should then have these properties. So this was put into this CRISP-DM model, cross-industry standard for data mining, cross-industry standard process for data mining. And you can take this as a kind of a high-level view of what you have to do in knowledge discovery, but also in data mining. So this process starts here. So this process, by the way, has been conceived in around 2000. And it was basically collecting experiences people had made in the decade before and try to make it a little bit systematic. And at which point do you start? At business understanding. So business understanding means you need to understand the problem that you try to solve. You need to understand what does my customer want to achieve. Maybe you're your own customer, yeah, because you want to come up with a new service and then sell this service. So maybe in light of learning or data mining, you're your own customer, but you need to understand your business. And this business understanding may be quite far away from understanding the pure machine learning algorithm. Yeah? So what does a medical doctor really need in order to be able to use a particular algorithm? It's not so straightforward. It's also very hard to teach here in this context because one really needs to look into the details of the application. This may include also other requirements, like how fast must the algorithm run? Or how much resources may I use? Yeah, if you build something as an embedded module into a car, you cannot consume 1 kilowatt yeah, for your algorithm. That would exhaust the car too fast, too quickly. It may also include quality that you require for your application. Yeah, quite often people say, I have a very difficult problem. Please solve this for me with machine learning. And then you can say, okay, I can solve this, but the quality I will achieve will be 90% accuracy. And then the question is 90% accuracy good enough for the application case at hand? So if you build an autonomous car and 90% of the time it's successfully able to stay on the street and not run into other cars, that's not very good, yeah, because the remaining 10% will happen too often. And of course, this may vary in different applications. So then, once you know what really is the target, you need to understand the data. The data is always awkward in realistic scenarios. The data typically contains mistakes. I talked about this last time. When you give the task to people to label data, for example, to say, what is a cat, what is a dog? After some time, people will do mistakes. Then, when you have this data, you need to prepare it for your algorithm. The algorithm is here. You define your model. And this is the part that we will talk about most in this whole lecture. This is the focus where you will learn about what algorithms do we have, what kind of models can we build with them, and not every model is equally good for all kinds of data or for all kinds of business purposes. But when you have data in one way, then maybe you have nominal structures, as we had last time with the shoes. Yeah, we had nominal attributes like red or blue. Maybe for neural network, you have to turn this into a numerical vector. So you need to prepare your data. I mentioned last time, maybe you have outliers, so you will need to reduce data. Maybe you have missing data. Sometimes you can use missing data as a feature, and sometimes you will have to substitute missing data by something else. And then you do modeling, and when you have a model that describes your data, your prediction, your regression, whatever, you will have to evaluate this. And you will have to think about the evaluation actually already at this point. Because you cannot just use all your data and evaluate on the same data. We will look at this in more detail. And quite often what you will find is that then you have to circulate, you have to go back to the business understanding because you do not achieve what you really want to achieve or what you thought would be useful. You show the result to someone and the person says, that's not what I wanted. Yeah? Or even if it's what they wanted, maybe it's not the quality that they were able to live with. And so you have to change the process. Of course, you could have also shorter cycles. Maybe the quality is not good enough, so you go back to modeling. Maybe you exchange a model, then you have to do a new data preparation. Maybe for that you need a better understanding of your data. Very often that's neglected here. This is a little bit outdated. You need not only to understand data, because this assumes that the data is already given. Very often you have to think about how to collect data. Yeah, when you now go to a company and they tell you, we want to have a solution with machine learning, very often they don't have the data they need for this solution in order to apply machine learning. Typical scenario, so one of our PhD students works for Trumpf, and I think they are quite sophisticated, and they want to classify whether their machines run normal. Well, they do machines like using lasers to cut blech. Sorry, forgot what the English word. Sheet metal, yeah. So they want to cut sheet metal. Thank you. And then they want to monitor whether the machines run smoothly and as expected. Now, in order to learn the difference between running smoothly and not running smoothly, you need to observe the machines in the wild. So they need to observe the machines at their customers. Now they have about 10,000 machines sold to customers worldwide, so expensive stuff. But now you need to bring data back from the customers. Now, maybe the customers don't want that you take data from their side and bring it back into your into your own organization. So you need already to change the contracts to be able to bring this data back. And of course, then the contract is something like, well, if you give me data, I can give you better information about how the machine is doing. But it needs to be already as part of the contract. And the machine must have facilities to collect this data, so then you can observe something about it. And then, of course, these machines do not just run in Germany, they run in Australia or Brazil or India or wherever. And there are different climatic contexts. Maybe it's warmer, more humid, or less humid, or colder, whatever. And so you cannot easily transfer results if you don't have these contextual variables. So maybe you need more sensors to understand how the machine is operating. So the whole thing of trying to predict whether the machine runs smoothly then involves a whole strategy from having contracts with customers, to attaching new sensors, to sending data back, which not always is possible. For example, we have collaborated with one company who had ships, and then when the ship is on the way and monitors data, it cannot send much data because that's too expensive, so you have to collect data, and then only when you're in the harbor, maybe you have a good connection to be really able to send data back to the company, who in this case was selling the propellers. So there's, you can say this is business understanding, but it also means data collection, so you can understand the data and work with it. And when you think of like even autonomous cars these days, they produce so much data, you can basically not send the data back. Just because when you have a sampling rate of 100 hertz and you have 100 different electrical devices in your car, and you can imagine there's too much data such that you could send it over via mobile link for an affordable price. And in the end, you will deploy it. That depends, of course, also on the infrastructure. So at that time, when CRISP was around, deployment mostly meant that software was shipped, let's say with a CD, and then from a CD read and deployed onto the computer. Nowadays, you try to do everything, of course, by servers on the internet, but that's not always possible, like in the ship example. That would not be possible. And so you need to think about the deployment infrastructure to bring the software to the place where it's needed. If you can have a server, that's maybe the best way to do it. So, and for each of the different tasks that I now explained, there are checklists. I think they're sometimes a little bit boring to go through in detail, but once you have a practical application in front of you, it makes a lot of sense. You read this CRISP DM report, which is for free on the internet, and to go through each individual place. For example, data understanding, Start with doing a data report. What are the extreme values? Are you surprised by these extreme values, or are they within the expected range? What's your distribution? It's always good to look at your data. What I see very, very often, the first thing people do is they visit this wonderful machine learning lecture and learn so many algorithms, so they throw algorithms at the problem. And this is as bad as you can do it. What you really first need to do is you need to look at the data that you have and understand whether this data has some awkward behavior. Maybe the data is not even good enough. Maybe you want to check whether people were good at labeling the data, or maybe you had an unmotivated worker and this worker just produced garbage, right? If you do some crowdsourcing, this happens. People want to earn money by clicking on crowd work. And if you don't control for the data quality by maybe comparing different annotations, then you will just have a lot of data garbage. And this is also true in other contexts. Yeah, data preparation, I mentioned briefly, depends a lot on the models that you're interested in. And we will talk about evaluation in a bit more detail in not so far ahead slides. Deployment is a big thing and even has become a discipline of its own. I think it is one of the next slides. Where you do not only think, do I deploy and how, but you think about how often do I update my deployment. Yeah, if you think of some large server-operated companies, whether that's Amazon, Google, Meta, whatever, they do a very frequent deployment of their software. And then, of course, often they just deploy it to a small set of users, so 1%, well, 1% of 100 million is still then a million people, and then test it whether it works with them, and then roll it out to all the customers. So for this you need to have quite elaborate plans and software engineering strategies to do such kind of deployments. With regard to the models, we will see many of them. Just to give you once here already the flavor why we do different algorithms. This is always in these 9 pictures the same data. And what you want to do here, for example, is to classify into red dots and blue dots. And from the label data, red versus blue, you learn how to form a classifier. These are abstract dimensions, but pick any problem that you like, and you can describe it like this. And then the different algorithms, the different machine learning algorithms, construct different borderlines for distinguishing red from blue. Tumor from non-tumor, for example. And we will today look into nearest neighbors. But you see, depending on whether you do this or this or this, the boundaries between these different pieces of data will be very different. And now it depends also on the problem, what kind of boundary drawing mechanism is best suited to your kind of problem. And, the term that dropped my mind just one slide ago was the term MLOps as a process, machine learning operations, where you have a more nuanced picture of deployment. You see when you do develop models and deploy models, people have refined this old CRISP-DM model for bringing machine learning algorithms into practice and have conceived MLOps strategies. And they have also distinguished different roles that a typically interdisciplinary team has, which needs to include the business experts or the business team that define the problem. Like in an insurance company, this might be the insurance experts that try to sell certain products. And the domain experts, they might know how this is handled in an operating system they have already. A data engineer looks at extracting, transforming, loading the data, especially if you have really large data. This may already be an issue, so you might have a database expert for that. Then you have a data scientist or a machine learning scientist to create the models. So here you will look into these kind of models that we learn here in the introduction to machine learning, and do the data pre-processing as required by the model. DevOps deploys the models on these various platforms, and the ML architect, is one who sort of keeps the overall picture, and every time you do an integration, some front-end design, etc., you need software engineers. So this is a more complete picture of the landscape you need in order to bring your machine learning applications into practice. Okay, so this was slide deck number 1. Any question up to here? And by the way, if you couldn't attend last time, please look at the recording, and especially also the well, non-content things that are said about the organization and how everything is organized for this lecture and the exercises. So let's now move to the next slide deck, where we talk a bit more about content. So let's look at classification. We've seen this last time, so I just go very quickly over it. Classification could mean you have objects and you want to identify the spam, or you have fruits, you want to classify this as peppers rather than apples. You have incoming documents, like insurance companies have that they scan everything and then it should be routed to the right kind of department. Or you have certain kind of assets and they should be classified as being highly speculative or other solid investments. So when we have classification, we look, or we want to have a method that assigns labels to our object representations. So these might be objects. And what we are interested in is a function f, and such that when we provide an object to this function f, it returns the corresponding label. Well, of course, it should, for this, return the label grapes. And such a classifier, f, is just a function. Yeah, I mean, that's what machine learning works on. It basically works on the mathematics. And also many of the tools like PyTorch, etc., they support of thinking in mathematical structures like functions and matrices. And so that's our language for talking about these problems is mathematics. So our classifier f works on objects, and each individual object is described with a list of m attributes. So xi consists of these m many different values. And as said, most of the time I talk about vectors. So all of these entries are numbers. And sometimes we have to do extra work to turn non-numbers into numbers. And we have here a corresponding attribute set. I mean, if you think of relational database tables, these would be columns from your database. So you describe a specific object. You can imagine this as a tuple in your relational database. So of course, it need not be a tuple. It could be an image, and then this would be the different pixels that you have for your image. And then we have a set of category labels. These are predefined. Like in this example for classifying fruits, you would have grapes and apples and oranges. And then the classifier f is a function that maps descriptions of objects onto category labels. So the function maps from the space of possible inputs to the space of possible outputs. We can even understand this as a kind of probabilistic assignment of mapping from one random variable to another random variable. That's what we will do when we look at probabilistic machine learning representations. And probabilistic machine learning is super often very useful because it gives us a mathematical tool, namely probability theory, to talk about these problems. And that's what's done very often. So the f we are interested in does such a mapping. This is the signature, the input type. The input type is described above here, and all the objects we will ever encounter fit into this, and it maps onto the set of labels. So these objects, these are the objects. We cannot describe the object like this. Maybe we have a description like this. We will have to turn this into numbers. I don't do this here on this slide. And we have the labels. And then there are infinitely many ways to model this function f. Well, if it's a very simple problem, you might even just write some if statement. Yeah, if it's red, it's an apple. You could try to do this. And of course, for simple cases, this would just be fine. But of course, you typically apply machine learning in those cases where it's very hard to write down such an explicit if statement. So what we want to do is we are interested in those problems where it's too hard to write down such an explicit if statement, or if then else, and so on. So you try to learn the classifier. And what we assume as input is that every individual object that we have encountered in our past already has some label. And what we're interested in is we want to learn such a function, f hat, as our output. So the machine learning algorithm takes for learning a classifier or for learning a regression as input these labeled objects, and as output it returns this function which works as a classifier. And when we now have new objects that were not seen here, this function can give us a label. And what we want is that it gives us the correct label. So learning a classifier means learning this thing, and then running the classifier means seeing new objects that were not here and returning the right label, or the right label in most of the cases. It is really, really important that we are interested in considering new objects, because if it would be exactly the same object, we would only have to remember. But of course, what we are interested in, we want to generalize to unseen objects. Yeah? I mean, if someone passes by here on the street, some living being, you do not have to have seen the living being in order to classify it as horse or human. Yeah? You intuitively can recognize this, you generalize from previous experiences. And then I try to use a convention that's frequently used, so not always, that I use this f hat in order to mark the function that we learn. And why f hat? Because what we typically do is we assume that there is a true function, the function that's unknown to us, and this true function is unmarked. It's f. So quite often, I mean, when we do this later on for linear regression, we will say there is a true function that generates data in this way. We don't know this function, but we want to learn a function which behaves almost the same as the true underlying function that is unknown to us. This is a way then of structuring the problem, of thinking about this problem in a mathematical way. And this is just has turned out to be very useful over time. And this learned function f hat predicts a specific value y hat for a specific x, whereas the true value or the true label for a particular input would be described as y. So when I said here, we have here, where did we have this before? Must have been the last slide deck. I talked about x and y's. Okay, now how do we get from this input to this output? So I have to be a bit more precise. So how do we do this in the general case? This f hat is not completely random, but it is produced from a family of functions, f. And the specific f that we look into is an element of this family of functions. So which family of functions do you know? Any suggestion? Linear functions, exactly. Yeah, we will do a lot with linear functions. Very simple tool, brings us very far. Other functions? Exponential functions. Yeah, exactly. So we could even have constant functions. Yeah, actually, in some places we even use constant functions. We just learn a constant for a particular decision. Linear functions, of course, and you see here my f hat is in this family, and I describe it in the end by the family it belongs to and by parameters. So for a constant function, I just have one parameter, the constant c. For a very simple linear function in one variable, I have one such slope plus a constant. So I have two parameters. And of course, when later on we will use matrices and vectors, then of course we have many, many more. And of course, when you look at ChatGPT, you have trillions of parameters that you have to find. Exponential functions, etc., etc. So basically, the core idea is, whatever you do, you define a kind of family of functions and then try to describe your function following this particular paradigm. And now there are many, many different ways of defining the family and then constructing the particular parameters. Okay, and when we have this, so what do? We have here this input. We have this family of function that people have thought out already. Maybe you come up with a new one, but that's very rare, but it happens. So you have this family, then you have a learning process, and this is then the machine learning step that as an output produces the classifier or the regression mechanism, such that when the new objects come in, they are correctly classified. Yeah, so the core questions of ML are, which form does my function f hat have? Well, I pick, for example, later on linear functions. And how difficult is it then to do this learning process? That's something we will have to look at. Or if I pick other kind of functions, like additive approaches, then I have a different learning process here. So each learning process then has to determine the parameters for the particular family of functions that I choose implicitly when I choose a particular machine learning process or machine learning algorithm. So let's look again at the task of learning a classifier. So we have our objects. So x1 has a label, x2 has a label, and xn has a label. We will always assume that our data is a sample from the two random variables x and y. Now, what does this mean? When we have here these fruits, then you know that all the apples and oranges always look a little bit different, right? Basically no apple looks exactly the same as the other apple based on color and shape, exact texture, exact colors. So every apple is a little bit different, like every human is a little bit different from the other human, right? And so each individual apple will have a different description. Well, let's assume this will be pixels. No apple basically would have exactly the same pixels as the next apple. And we would have for a particular fruit a label from our set of possible labels, for example, apple or orange or something else. And that we say this data is sampled means that from the world of possibilities, we produce with certain probabilities certain kind of apples. So for apples, it's quite normal that they're almost round. I've never seen an apple which was like a stick. So, I mean, maybe it's not even impossible. I mean, certainly we could start growing breeding and then growing apples that are more lengthy, more like pear-like. It is possible, but it's less and less likely if you just go to the supermarket that you will have such a kind of apple. And of course, once it's very thin and very long, it's definitely no longer an apple anymore. Yeah, so you can think of that a prototypical shape of an apple and a prototypically pixel representation of an apple should be a more probable sample from a probability distribution of apples. And the same is true for oranges. And oranges and apples are different, and the mixture of the two is also a very unlikely construct. Maybe more likely than something else, than a mixture between an apple and a camel. But yeah, you get probability distributions over what you expect in your space of objects that you encounter. And the same is true, of course, for the labelings. You're interested in the joint distribution. That means you are interested in how are certain pixel combinations, depicting apples or oranges, labeled with labels such as apple or orange. And maybe sometimes there is even a mistake in it. Maybe the mistake happens when the orange looks almost like an apple or the apple almost like an orange. So you have a probabilistic assignment of this data, and then we can talk about this with probabilistic tools. Okay, so we have objects. Here it's just like, symbolically described. Some vector with apple, some vector with orange. This is the joint distribution of random variables, x and y. And now we have our family of functions. We find that function such that this function maps from the Cartesian product of the attributes. So we have a first attribute like color. Well, color, you could even think of RGB values in terms to have it as a numerical depiction. The second one would be some shape. Maybe you have some shape measurement. People in computer vision have thought about such primitives. Well, not in use anymore, but you can think of it like this. So the second attribute would be a shape value describing how round something is. And the last one would describe the texture, like smooth or rough. And correspondingly, you would have some numerical value for that. And so that function should take this Cartesian product of the possible attribute values and any particular object that's possible within that map onto a label. Now, when do we have a good function? When have we found a good f-hat? Well, we have a good f-hat if we minimize the so-called empirical risk, or also called loss, on the data that we have observed. We have seen here examples. And what this says is nothing else than on our examples, our function f-hat should do the right thing. It should classify correctly. And if it classifies the examples incorrectly, then it's not a very good function, right? Rather trivial. Of course, in order to turn this into a mathematical framework, we need to describe what is this loss here. Yeah? And what do we do here? Well, what we do here is we compute the loss for all possible functions that make a prediction on our input and see how this compares to our label. This is our label. This is our input. This possible function turns this into a prediction. And then we compare whether the prediction is close to the original true label. And if this is the same, then the loss should be 0. And if it's not the same, then it should be different from 0. And the more different it is, the worse we are. And of course, later on, we will even do some modifications of this. So even if they are the same, maybe there are situations that are to be preferred or dispreferred. And then I do this for each individual object. So I count over all my example data. Yeah, this is my example data. I go over all my example data. I calculate for every individual training example how good my function is. And if it's perfect, then I might have here a loss of 0 and I just add 0 n times. That would be an ideal situation. And if I find a function that does that, then I take this function that minimizes this sum. This is what the argmin says. Argmin is this function that says everything down here that is in this family is evaluated, and then you pick this f tilde that minimizes this term. You take the argument that minimizes this term. This is the argmin, very important operator in machine learning. And this is exactly the f hat theta. This f, of course, will be described by the structure like a linear function plus the parameters. And the parameters are summarized as a vector theta. So the f hat theta of an object description should reproduce the original observation yi. So if I give this as input, this should be produced by this hopefully good function. What I recommend for you to do is every time we have seen a new algorithm, go back to this slide and see how it aligns. Okay, so what do? We minimize the loss. What would we do in the best possible case? I said already that we describe all possible apples, and all possible apples are represented by this random variable that stands for how can an apple look like in our description. And we consider this to be a random variable. And we look like how are the labels for these different objects, and we are interested in such objects that are sampled from the true underlying distribution that we don't know, by the way. This is a thought experiment. We think that what if for all possible shapes of apples and all possible label assignments, how does this pair look like? And when we take this infinite number of apples and corresponding labels and infinite number of oranges and corresponding labels, then we are interested in this function that minimizes the expected loss. What is the expected loss? Expected loss just goes over all possible examples and computes the average. And so we want for all possible examples that could ever come up with a certain probability, minimize this loss. And then we would be perfect. Well, as good as it could be. Maybe sometimes we don't have enough information in order to classify two different things. I once was an advisor to a project and they wanted to classify fishes in the South Chinese Ocean. So they had some cameras that would just record, like 10 cameras, record the fish and other animals or things that would come by, and they wanted to automatically classify it. And for some fish you can do this nicely, and for some species you cannot distinguish them just by video. You would have actually to take them out of the water, take some biopsy and look at their genes in order to distinguish them. So in such a case, you have two different species, right? Two fish, but they just look the same. So even though they have different labels, different true labels, you don't have enough information. You would have to have gene information and you only have video information. So you will do a mistake, because even the best possible function cannot provide the right label. That's, if you ask me, here's a flock of sheep, please tell me what are the, I don't know, good or bad sheep in this family, or this flock. Yeah? And I couldn't tell. I'm not a shepherd. So that's what we would like to do. This is the mathematics. We want to minimize this loss. That would be our target. Now, what do we do when we do machine learning? We cannot go over the true expected, we cannot compute the true expected value. All that we can do is we can compute the empirical loss. What is the difference between the empirical loss and the expected loss? This expected loss goes over all these possible instances, and the empirical loss just takes the training data that we have. The training data is not the full true distribution. Right? It's a bit like I would say, okay, I want to learn something about people, so I just observe all the people here in this room. Yeah, we have a certain sample of people, but for example, in this room, there's no one that's 5 years old, at least I don't see anyone. There's no one that's 80 years old here, at least if you are, well done. Couldn't figure this out. So you are not a representative sample of all of humanity, right? Of course, we also don't have people from all over the planet. Yeah, we have diversity, but not from all over the planet. So you would be like an empirical sample that's biased by whatever mechanism led you here, and you're not representative for everyone on Earth. Okay? And this is often the case. And so in order to approach the very best function that would come with minimizing the expected loss, all that we have is that if this n becomes very large, then we can hope to approach this. So as the n goes to infinity, we approach this expected loss. But on this left side, we always have this empirical loss. Now the empirical loss, if I learn something about you, whatever it is, how I would like to classify you. Maybe I would like to classify you into genius and non-genius, yeah? And then want to apply this classifier for whatever awkward reason. Maybe I would be the bad man in a James Bond movie, a villain, and I would like to do this. I would not be able to learn with you as a sample the true differentiation for genius versus non-genius, even if all the labels I would have about you would be perfect. Because I would not observe the full data that I would need to observe, really. And now what happens? My machine learning algorithm will minimize this here, obviously, and this minimization will not be perfect because I will not take into account the 5-year-olds, the 80-year-olds, and maybe they have a different characteristics for being a genius. And so that means I will overfit my optimization on the sample of data that I have. Overfitting meaning I will try to be as close and perfect for the data observation I have here, but I have to ignore everything I don't know. And with whatever algorithm I choose now, I will always do a mistake because I don't have a perfect sample. A perfect sample would be infinite sample, so that would not be tractable anyway. And so I will overfit to the data that I actually observe. That always happens, even if the representation is much better. I mean, if you maybe a good representation for students at University of Stuttgart, yeah? And even then, when you're a good sample out of all students of University of Stuttgart, even then you are a sample, and every time you take a sample, it's not the perfect distribution. When you throw a dice 600 times, what would you expect? How often comes the number 6 up? 100 times. That would be a perfect distribution. But when you do it actually and you throw it 600 times, very often, maybe it comes up 101 times or 98 times. So it's very rarely that it comes up a perfect number of times. Yeah. So therefore, when you learn it, you deviate. And this also is a mistake. You don't learn the right percentage, and this is overfitting. Okay, so now we have our core machine learning mechanism from an abstract point of view, and based on which actually the theory of machine learning, which we don't really do here, I have to say. Theory of machine learning is quite a different piece of cake. Very interesting, but we have no course for that, unfortunately. So we always have this same kind of empirical loss formula. And now this empirical loss formula has different ingredients. So I talked already about this f coming from a family of functions. That is the first ingredient. You determine the family of functions, linear functions, decision trees, KNN, etc., etc. Then the second ingredient is the data, the xi's and the yi's. And you can think about, is my data of good quality or poor quality? Is it representative for what I want to learn? Or is it just an awkward subsample? Is the data indicative enough to distinguish the different fishes? Or is really the visual perception of the fishes not sufficient to distinguish that they come from different species? And then I have a loss function. I have not really described to you how the loss function looks exactly. And we will encounter different loss functions. And you have a minimization. And how do you do minimization? For minimization, you need an optimization procedure. And so every machine learning algorithm does optimization. And how you do this exactly leads to different results. Yeah. So these are the core ingredients that you will always need in machine learning. You always need some model or some family of functions. You always need data, and the data you can maybe even augment. That's what sometimes is done. We will talk about this in when we look at classifying images in convolutional neural networks. You have different loss functions, and you have different possibilities for optimizing your parameters. And you can combine this also, right? You can change several places at the same time. Again, my recommendation to you, when you have seen a new algorithm, come back to this slide and check whether you can sort of like identify the different parts. I will tell you it's not always easy. Actually, even our first example is a not very good representative one, but the first example algorithm is chosen for the fact that it's a very simple algorithm. but it doesn't fit very well into this frame. The second one will fit very nicely into this frame. Okay, so what do we need to know about machine learning? Learning means we have data, we have a representation, family of functions, we look at some sort of evaluation and an optimization. So that's a different way of summarizing the slide before. So now we look at our first true machine learning algorithm, which doesn't fit in neatly into this description, but sometimes it's quite useful just to have a simple baseline. This is a very old algorithm. It's very simple to implement, to understand. And what you can always do when you build your second algorithm, you can run it against the first simple one. That's always a good practice. So, and what you have when you have an algorithm, you have to look at when is my algorithm good, and you want to do this by checking against different types of data. Maybe your algorithm is good for one problem, but not very good for the next problem. And it's also good then if you can test drive with data sets and you don't have to collect the data sets, because collecting data sets is a lot of work. And so we look at some examples from the UCI Irvine dataset, and one that you will see several times is the mushroom dataset. Actually, just a subset of the mushroom dataset. And what is the mushroom dataset? It's basically a description of mushrooms and the classification, whether they are poisonous or whether you can eat them, or whether you can eat them but they don't taste very well. So you want to seek out some and not have others. And if you're ignorant like me, you cannot really distinguish the mushrooms, and you would rather have some reliable classifier before you start eating. So how do you describe your mushrooms? For example, by the cap. So, I mean, you can imagine here that You pick the mushrooms in the forest, come, and then you can describe, the cap of this is maybe a bit rough, or the gills here are dark, and you have different kind of attributes that you describe, and then you classify based on your visual perception and based on your own visual perception of the particular type of mushroom that you have in front of you. So the mushroom data set, the subset, has 100 objects and 8 attributes, and category labels, eatable or poisonous, and well, it's abbreviated here with edible and poisonous, and the prediction task is to classify the unseen mushrooms. And by the way, here is the full data set from the UCI Irvine collection. The original data set has more features and more values. Not only edible and poisonous, it had this in between. This Fliegenpilz, I think in German it is like, you don't die from it, but you don't like it when you eat it. So much I learned, but that's about it. Okay, so here are some examples, here or the attribute descriptions. So that's what you need to understand for any data set. Here the attributes are the cap shape. Here there are 4 different values. All are abbreviated with 1 letter. If it's bell-shaped, then it would be a B. If it's convex, X, flat F, sunken S. And likewise for the cap surface, the cap color, there are 4 different colors here, whether they are bruises or not, whether the gill spacing is close or crowded. So I wouldn't be sure how to classify that. So we need to see some examples of the gill size, color of the gills, and the habitat where you found the mushroom. So this is your attributes with the possible attribute values. And now a typical data set might look like this. It's a comma-separated file format, and every row here is 1 example mushroom. And in this specific case, I marked it here that the target label is the first entry, but that depends, of course, how the data looks like. The first entry indicates poisonous or edible, and then comes the X. So, I mean, we discussed before, the object is the XI, and the label is the YI. Here the label YI is at the beginning, and then the rest here is the object description. And so that's basically your training data. And of course you see here more than 8 attributes, so the other attributes are just not described in what I showed you on the slide before. So the first thing, as an example for data pre-processing, is you have to turn your nominal vector into a suitable vector representation. There are different ways to do this. For example, we had here attribute descriptions, bruises. You could have bruises true or false. Or you could have gill spacing, close or crowded. So in such a case, you could distinguish, for example, say, in this dimension, I distinguish no and yes. No and yes. And of course, even you also had other attributes that had, for example, 4 different colors, 4 different values. Then you have to think about how to describe it. One way is that you, for example, turn color into several dimensions. You could say, okay, are the gills black? Then no or yes. Are the gills brown? No or yes. Are the gills green? Would be another dimension, and so on. So you might have very many dimensions. There are other better mechanisms like target encoding, but let's ignore this here. And when you now see your example data, so for example, this example X3 has no black gills, and in the second dimension maybe no brown gills either, and it's poisonous. And this example X2 maybe has brown gills but no black gills, and it is edible. This is the label Y. And here is the first example, which has black gills, no brown gills, and is poisonous. And of course, we would expect to see many more examples like this, and much longer vectors, not just vector in 2 dimensions, but vector in maybe 100 dimensions. And this is now a vector representation that we can work with. So KNN, or let's start here with K being 1, so 1 nearest neighbor, is a very simple learning algorithm. It doesn't even learn properly because it's so lazy. It just represents all the objects in the vector space. And then the function is basically consider the most similar neighbors and pick their labels. I've described this now with text because it gets a bit unwieldy if I do this in mathematics. I can do it, but yeah, it wasn't so important here. And so if these are training examples, and this is the function, you basically separate the space into influence regions. You could actually here you have a kind of a Voronoi tessellation. And this Voronoi tessellation of the space describes what is the influence region of this point, of this point, of this point. And you see there in the middle between these 2 points, there is a delineation. And if the point is close to x2, then you classify it as edible. And if it's closer to x3, then you classify it as poisonous. Now, here it was bell-shaped, not brown-gilled. Of course, you have either yes or no, there's nothing in between, but you could imagine that if you take the size of a mushroom, there could also be values in between. And when you think of, you don't have 2 dimensions, but 100 dimensions of yes or no, then you would also have distances that would require such delineations between example mushrooms. And of course, you see, you do not only have such kind of straight line, orthogonal lines, but sometimes, like between this part and this part, there is a kind of a diagonally oriented line. And as soon as you are on this side of the line, the point is closer here, and on this side of the line, the point is closer here. So the learning basically just means you have your examples, and as soon as you want to have the actual f, you compute the nearest neighbor. So f is the yi. Yi comes from the training example. X is a new object, and this is this label where the object that you have seen before minimizes the distance between your new object x and the old object from your training data set. And here we choose the Euclidean distance, the squared Euclidean distance. Well, and x is a vector and xj is a vector, and just square the distance. We don't take the square root. And so if a point would be here, you would find out, this is the next point, and I would take the label that is available for x2. And that's it. Really stupidly simple algorithm. Of course, there will be questions like, what if something is exactly on a dividing line, and maybe you assign it here, but then it might be poisonous, then you feel sorry afterwards. So be careful about this. And of course, you can think about what is actually the loss function here. So when do you do a mistake? For your training examples. And well, here the loss would be actually, for example, the computation of the distance between the label that you predict and the label that was given. So for this, of course, also the label must be numerical, like 0 and 1, and not yes and no, or poisonous and edible. It must be also some sort of numerical label, so you can actually do this. Now, what is nice about nearest neighbor? Well, it's effective. It represents our objects in vector space. What is quite nice about one nearest neighbor is that automatically I have a loss of 0 on my training data set. Because every example I give is closest to itself. Oh, is this now a good result? Maybe not, because the question is how well does it generalize? And the generalization could be a point here on this line. The generalization could also be maybe some example is close to an edible mushroom, but still poisonous. So you see already that when you have a perfect loss, it doesn't mean automatically that you do very well. And if you do badly, you can die if it's mushrooms. So be careful. What you do here with your loss function, you're not automatically very good just because your loss function indicates a loss of 0. You have to define some distance measure. Sometimes that's easy, sometimes it's not so easy. You have to define a loss function. We did both that. You also need to consider the efficiency. And the algorithmic efficiency of such algorithms depends on two algorithms. One is the algorithm for training. The algorithm for training in this case was very simple. You just have the list of examples. This is no effort at all. At worst, you can say, I load the examples into my database. That's a linear complexity because you need, for n examples, you need to touch each example once to load it into your database. That's very efficient. It doesn't get better. Well, actually, you can even do subsampling, then you don't even have to look at all examples. But you can do this when you have sufficiently many examples. But it's very good. Inference is not so good. Because for inference, you have to compute this. What is the closest neighbor that I have? And searching at the closest instance depends on your exact database strategy. So databases offer nearest neighbor search, but nearest neighbor search in very high dimensionality is also rather inefficient. So in the worst case, you have to look at every example and compute the distance to every example. This can become rather inefficient if you have to do this for a large data set. So what you want for inference, for applying your function, if you have a linear function that you apply, you just compute ax plus c. That's super fast. But here you would have to go maybe through a database of 1,000 mushrooms. So it's comparatively slow. And as I said already, maybe you don't do the best choice. If you have a loss of 0, which you automatically have for one nearest neighbor, you are still not perfect because you remember you can overfit. You train your data with a sample of all true mushrooms. Maybe some mushrooms take on a different color or look a little bit different than what you expect. And so you may have a loss of 0 and you may have overfitted on a particular sample that is not representing all mushrooms that could be out there in the world. And well, maybe between here is a space, maybe that should be classified as poisonous, but you classify it as edible in such a high dimensional space. It's very hard to see. So you cannot rely on this loss on its own. Overfitting, by the way, is defined or can be characterized that the label training data provides only examples and the generalization is required. And the generalization is about new and unseen data. And this is what your loss does not look at. The loss function does not look at new or unseen data. And in order to judge the generalization, you need to do extra effort. Just a few examples here. When you have blue dots and red dots, how do you classify this unknown dot? It depends how you form your boundaries. You could form your boundaries like this, draw ellipses around your red dots and blue dots. You could also draw boundaries like this, and then you just would know what to do with the gray dot. You could do it and this is what one nearest neighbor does. It basically says every example I know tells me in its vicinity what the correct labeling is, and maybe there is a place where I just don't know what it truly is. I would maybe compute this as a nearest neighbor, but maybe that's not a good decision. So overfitting is the effect that you cannot generalize well enough and based on the sample of data that you have. And the different algorithms, all of these three would be plausible algorithms, and this is 1 and n, maybe gives you bad performance on data that you have never seen before. One extreme example is just learn by heart. You use the object ID, then you don't generalize at all, you just re-recognize some pixel configuration you have seen exactly like this before. So many algorithms optimize loss, but only some are good predictors. So then you start to do things. And one thing you do with one nearest neighbor is that you say, we don't do one nearest neighbor, we do k nearest neighbor. What is the idea of k nearest neighbor? It's basically saying if I only have one nearest neighbor in a neighborhood, maybe that's not a safe bet. I rather look whether several neighbors in my neighborhood all go in the same direction. And this avoids overfitting at least something, because then you do not rely on the idiosyncrasies of a particular training example which just happens to be in a neighborhood. You look rather at generalizing patterns. So with k nearest neighbor, you would, let's say with k equals 3, you would consider all these 3 in the neighborhood. And then you could do different things with this k nearest neighbor. The simplest thing is to do a majority vote. Majority vote here would say, poisonous, be careful. You could, of course, even say, well, in order to eat it, I want to have only edible mushrooms in the neighborhood just to be on the safe side. So this depends then a bit on your application. You can, of course, also experiment with it and say, how well does my k nearest neighbor generalize? And then I pick among k neighbors those percentages that give me the best application characteristics. So here is another abstract example. If you have here a new data point, and here you have examples that are described as plus or minus, then this data point, here is also a plus, this is a plus, this is a plus. One nearest neighbor would say this is a plus. 2 nearest neighbor would say it's a plus. 5 nearest neighbor would include all these examples, and then would say it's rather a minus because it's 3 minuses and 2 pluses. So then, depending on how you choose your k, and your voting mechanism, you end up with a different classification result in such a scenario. Note that many of these scenarios look a bit awkward because I have to pin them here on a 2-dimensional slide. And when you think of all the attributes that the mushrooms had and the distinguishing maybe even of one attribute into several dimensions, we rather talk about 100 dimensions. And in 100 dimensions, these kind of awkward configurations are much more frequent than in 2 dimensions. This is always what you have to keep in the back of your mind. We always talk about rather high-dimensional spaces. So I can set the parameter k for different numbers, and I can look at when do I have good results. If k is very small, I do not generalize very well. As soon as I have an outlier, an apple that looks like an orange, although it is still an apple, then this disturbs my classifier. When I have k which is too large, then I generalize too much. Then all that is important is what is the majority of objects. Do I have 10,000 apples and just 100 oranges? Then I will classify everything as an apple. And a middle range is then the right thing, but what exactly middle is, you'll have to find out by experiments. So what you do is you probe, and for each k you determine the classification error. Now, if you do this on the training set, I said already that one nearest neighbor is perfect, typically on the training set. Not always. Again, with the fishes, two fishes that end up in the same point, you do a mistake. Yeah, that's other. So it's not always 0, but very often it could be 0. But you would not know how it generalizes to unseen data. So what do you do in order to generalize to unseen data? You separate the data that you have. You separate the data. If the data is here described in some way, you separate it into training data and into test data. You train only on this part, and on this part, you don't show this to your training algorithm. You test how good the algorithm trained on this data generalizes. And then you can also do this, change the role. You can also then train on this part and test on this. So you can change the role. What you have to be careful, when you train with data, you must never ever test with this data. Yeah, the testing must always be completely independent from the training set. And we will, I think next slide deck, next time, actually also look at validation data for yet another purpose. So, good enough for today. We see each other next week. Have a nice week until then, and